So today we have also the committee members, Adam, his advisor, as well as Eddie and Olivier. And without further ado, I'll let Batu start.
Right, sweet. Let me start my timer and get going. Okay. Right, sweet. Is my screen view shared okay?
Yes.
Okay, lovely. Hello all. Thank you very, very much for coming. It's actually a lot of fun to see all of the new faces and faces I know, mostly names. But today I'll be talking to you about my thesis proposal, Design Out Helplessness, AI Interventions for Game Inclusivity. Hopefully, as you know, I'm Batu, and I am from the Design Reasoning Lab at the Computational Media Department from UCSD, and I'm working with Adam Smith on this project. Right, without further ado, let's jump in. I want to start with some stories. Stories are important. The first story comes from 2019, before the end times. This story takes place in the AIDS conference in 2019. So we were at an in-person conference at Georgia, and this we were actually having dinner, and it was a lovely situation where this is an image of us humans having fun at an academic conference. And as you might or might not know, AIDS is a conference on games, AI in interactive digital entertainment, if I'm not mistaken.
Batu, I want to interrupt for a moment.
Yes.
There's some Zoom window you have at the bottom of the screen that we can see a little bit of, but it's obscuring some of the text. Like in the center bottom of the screen, whatever.
Is it better?
Like,
oh,
well, we can't see the UI element, but we can sort of see like a gray
I
rectangle that it leaves as a shadow.
Gotcha. Okay, so that was the subtitles. Okay, and if the subtitles are distracting to you, you can hide them in the Zoom menu. Right. Okay. Sweet. Okay. So yes, we were at the academic conference and we were having dinner there, and we were talking about the games that we had been playing at that time with the other conference attendees. And the conversation went on, and a waiter approached us, and he joined in the conversation. We kept talking about games, and at some point he asked us what platform we were using to play those games, and we said that we play using the PC. And he stopped for a moment, and then he said, "Oh, I would never be able to play computer games. There are too many keys." And it was interesting to hear, to say the least. So another story. That's me. And last Christmas, I think 2020 Christmas, I was back home, and I was having a conversation with my mother. We were drinking tea, as we usually do. And the conversation was about my future, my past, so a deep and intense conversation, to say the least. And at some point, I asked her why she didn't play games with me while I was growing up, because she knew that games were a big, important part of my life. I'm getting a PhD in games. And I was curious why we never shared that experience together. And she answered that question. She said, I didn't play games with you because games made me feel incompetent. And now on to our last story. This is a tweet from Tad Leckman. Tad is a faculty member at UCSC, and I work with him closely. I teach with him often. He's a game design prof. And he was sharing his favorite game from 2019, and that was Below. And I was very excited. I was like, cool, I am going to buy this game. I'm going to play this game. I'm going to chat about the design decisions that this game made. It's going to be an amazing time, and I'll connect to Tad. And then I started playing, but I only managed to play for 48 minutes. And this game is a much, much bigger game. And the reason why I stopped is because I couldn't figure out the game. I just couldn't make progress. I didn't understand what I was supposed to do, got stuck, and then I bounced off. And I couldn't share the experience of playing the game, discussing the game with Tad. And it was unfortunate because I felt a little bit dumb and somewhat incompetent. So in all these experiences with people not being able to play computer games because there are too many keys, people feeling incompetent, and people not being able to share the experiences, there's this feeling of helplessness. And when I say design out helplessness in my dissertation title, that's what I'm referring to. So my whole dissertation, my whole work is to ensure people don't feel this way while playing games. And yeah, hopefully when I make progress towards this end, we will see less of this. Okay. My advisor keeps telling me anecdotes actually don't make dissertations. So let's take a step back and then try to look at the literature about these type of topics. So there are more than 2 billion video game players. This includes PC games, mobile games, all types of games. And this goes to show that how big of a cultural phenomenon games are actually becoming or have become already. World Health Organization used to have a rather negative stance against games, but recently, especially with the rise of the pandemic, they started recognizing how games are useful in connecting us to one another. They started a campaign called Play Apart Together, and they advocated it for people to use games to connect to one another during these isolated times. And it is, a lot of research has gone into exploring how multiplayer games are a source of connection. Back in 2004, there were studies exploring the social side of MMORPGs. And it's common to recognize that people sharing in a space can connect to one another. But multiplayer games aren't the only ways people connect to one another using games. So from a talk in UCSC, Michael John, makes the claim that there are actually no single player games. And his main thesis in that talk is that even single player games are not necessarily played in isolation. And single player games are a big source of connection. People play games with one another, even though if they're single player or not. People actually create content, create fan art over the games that they play. People actually learn how to mod, how to program and create content for the games that they're playing. And interest groups emerge outside games. This is a video from Video Games Done Quick, where people are aiming to play games at a wildly fast rate. And when a game rejects you, you're not only rejected from the game itself. When you can't play a game, it's not the only game's contents that you're losing, but all these things that come with games. That's why it is important for us to ensure games are inclusive. Not for the sake of games, but we need to ensure games are inclusive for the sake of people who play them. And I keep saying inclusive. What I mean by that is the focus taken in inclusive design. So inclusive design is about developing a diversity of ways for everyone to participate in an experience with a sense of belonging. And the term inclusivity in my title actually refers to this definition. So I claim we should focus on making games more accessible experiences and more effective teachers to make them more inclusive. And I'm going to go deeper into each section. So, more accessible experiences. What do I mean by that? Disability, World Health Organization defines disability as follows. Disability is not just a health problem. It is a complex phenomenon reflecting the interactions between features of a person's body and features of the society in which he or she lives. This is a different perspective compared to the one taken earlier, back in 10 or 20 years ago, where disability was defined as an aspect of a person. Instead, a more recent understanding describes disability as a mismatch between the person and the context that they're in. So this notion of disability and this notion of disability actually fits very well with how diverse we are as people. I used to think of disability as the other type that I define as a permanent aspect of a person. So if someone was missing an arm, they were disabled on the aspect of touch. If they couldn't see, they were blind. If they were deaf, they had a hearing disability, and so on and so forth. But these are just a certain group of disabilities, which are permanent. But there could also be temporary disabilities. Someone might develop a eye illness, and they might, for the duration of that illness, have a seeing disability. Well, not of that, there could be situational disabilities, where a new parent who might be carrying their baby might be having a mismatch between the situation that requires them to use both arms. And assist nodes are the way games have been trying to respond to this diversity of our players. So here's an assist node from Mario Odyssey. What the assist nodes do is they allow the players to actually modify and customize the difficulty of the games. In Mario Odyssey, when you open up the assist node, deaths and failure becomes much less challenging. Instead of being teleported to the start of the level, you just bounce back to the place that you failed. And also some guides appear to help you go around your way. And I actually use the assist mode while playing games. to spare you some visual imagery, last month I broke my collarbone. So when I was playing Mario with only one hand, I definitely used the assist mode. So even though now I regained usage of my both arms, I was temporarily disabled through an arm injury. And furthermore, I actually use the Mario Odyssey help mode in a context where I was situationally disabled, using this terminology. I had a projector, and when I tried to use the projector during the day, the colors were faded out. So having the assist mode on actually helped me a lot. So making games more accessible helps everyone, not necessarily only those who we used to think as people with disability. And that's why I claim that we should focus on making games more accessible experiences. Now let's switch to making games more effective teachers and why that might be the case. So if you cannot learn to play the game, you're excluded. There's no more to it than that. A game needs to teach how the game is meant to be played to their players. And games traditionally do that through tutorials. Unfortunately, most video game tutorials suck. Suck meaning they're not very effective. And here are some examples of people talking about tutorials. Ray in 2010 says, no one likes tutorials. Onboarding vomit. Great tutorials are hard to come by, and bad ones are unfortunately in overabundant supply. We all hate in-game tutorials, the T word everyone skips, and so on and so forth. And there are many more references. And tutorials are important not only because they teach you how to play, but for inclusivity aspects, but they're also important for many other reasons. One is commercial. Games that are being hard to understand is one of the major reasons for low attention, especially on mobile games. And people actually reconcile their expectations with their initial experience doing tutorials. And that actually allows them to decide whether they're going to keep playing the game or not. And there's a whole book on designing tutorials. And the central thesis of Learn to Play is that good tutorials teach how to enjoy the game. Meaning, if the tutorials are well made, then the player will actually have more fun playing the game. And there's also a lot more opportunity for research. Not much research has been done on tutorials. So Green et al. In 2018 on their paper called Press Space to Fire does a short literature review and describes the literature on game tutorials as you see on the screen. And this might be because there's a huge body of research when it comes to using games for learning. So that might be the reason. And also, the tutorials aren't necessarily only for making games more inclusive. Not only that, but a very prominent theory called theory of fun describes fun as a response to learning, which means if we can make our players learn in a more streamlined and in a more effective way, ideally, they'll be having more fun in our games. And a talk from Game Developer Conference on Mortal Kombat 11 actually breaks this down a little bit further. This is a whole talk on their tutorial mode. And one thing that they describe is how they're using their tutorials not only to introduce people to the game, but rather level them up and skill them up. Their data shows that the higher skill level a player has, the longer they play. And the longer they play, the better they get, most of them. So it is not only necessary for the game to teach people how to, be a starter or a beginner in the game, but rather they use their tutorials to actually guide the players up this ladder and keep people having more fun. And I think this is a huge opportunity that we can actually work on, and not enough people are talking about this skilling up aspect. But at the end of the day, if you cannot learn to play the game, you're excluded. And that's why I claim that we should make games more effective teachers. And I claim we should do these things using AI techniques. So why should we use AI techniques? There are two main reasons. The first one is that AI techniques helps us respond to the diversity of our players, as we discussed. AI techniques are really good at customizing the responses that the game gives. So using AI techniques can allow us to respond to different needs of our player base. And furthermore, being able to play a game is very useful in assisting our players. And there's a huge body of research about how to play games effectively. So we can utilize the pre-existing research and actually use it in our games to help people. And that's what I mean when I say AI interventions in my title. Okay, so let's formalize this just a little bit more. I have two research questions. The first one is, what lenses on games and the game design process will allow us to improve inclusivity in games without negatively affecting the design intent? And the second question is, how might artificial intelligence techniques be used to intervene in game designs to design out the feeling of helplessness and exclusion effectively? So let us look in my past work to see what I have done about these two research topics so far. But before we go into that, let's take a short break and watch this relaxing GIF while I take some water and tea. I find this GIF very relaxing. I hope you agree.
Oh no.
Okay, neat. Now that you're sufficiently relaxed and ready to get into my past work, let's jump right in. So I separate my past work in two groups. There's theory work that I've done, and there are certain AI interventions that I've implemented. In the theory side, I have a paper on taxonomies of failures, and also another paper that describes how we should repurpose game AI for inclusivity. And on the intervention side, I made some work on tutorials, and there's a tool that I created called SNES. And later down this presentation, I'll be talking about my proposed future projects. So this whole group is the scope of my proposed thesis. Let's start with taxonomy of failure. And this was presented at FDG 2020. So as we talked about, failure is a necessary component of games. Not all games, but many. Here you see 4 games that have failure as a core component. Dark Souls is provably and markedly very difficult. Darkest Dungeon similarly so. Rogue is a game that started a whole genre called roguelikes, and a big point of this genre is to fail and try again, and getting over it is a meditation on failure and difficulty. So these games are especially about failure and difficulty. But even games that are not explicitly so, like Mario, have a lot of failure. In Mario, you try to make progress, you fail, you learn what to do, you get better and carry on. So failure is important, but not all failures are good, right? Some failures actually makes us respond to this like this, especially failures that are outside of our control. And for example, if I die because I have color blindness, and I could not differentiate the enemies from allies, and I failed because of that, that's not really a good feeling. So some failures are good, seems like, but we need to know which ones and how do we tell. And this paper tries to answer both of these questions. So let's start by deciding which failures are good and which are bad. And in order to decide whether a failure is good or bad, I'll be describing these two terms, an in-loop failure and an out-of-loop failure. So let's see what those are. Imagine you're playing Jenga. And for those who don't know, Jenga is a game where you're drawing blocks from this tower and then placing them on top. And whoever topples this tower fails. Let's assume you drop the piece. You're playing Jenga. This is a physical manipulation failure, right? Like you were actually pulling the piece, but your dexterity capabilities weren't up to scratch and you dropped this piece. This is not a design problem. And the reason why this is not a design problem is because the failure supports the core gameplay loop. And what I mean by core gameplay loop is that what the player does throughout the game session. And failure is basically, this failure in Jenga is furthering the idea of the game. The game is about physical manipulation. So when you drop a piece, it is not a design problem. You might still lose the game, but no problems with the design. Now let's look at chess. And imagine there's a alien-looking weird new chessboard. Once again, you drop the piece. It is similarly a physical manipulation failure. You're trying to move the piece from one place to another, but it fell down. Like you failed at accomplishing your goal of moving the piece. Now that is a problem with the chess set because the notion of dropping a piece is not necessarily supported by the core gameplay loop. The chess is not necessarily about moving pieces or being able to move pieces effectively. It's about making plans and counter plans and executing on them. So the same type of failure, dropping a piece, is not a problem and as such an in-loop failure in Jenga, but it is a problem because it's an out-of-loop failure in chess. So to be more specific, an in-loop failure is failures that are expected to happen in the game loop. And similarly, out-of-loop failures are failures that are not expected to happen in the game. So during a playtest, if you see an out-of-loop failure, you as the designer should take action to remove that. Okay, so in-loop failures are good and out-of-loop failures are bad. But how do we tell? How do we tell which failures are in-loop and which are out-of-loop? For that, we actually look at the different classes of failures. And for me to explain that, I want to explain a model of how people play games. So when you're playing a game, you have a mental model of that game, meaning you have an understanding of how the game functions. Using that mental model, you actually make a plan. Let's say you're playing Super Mario. Your model of the game includes how the character moves, how Mario moves, and your goal. So you can say like, okay, I'm going to jump on that Goomba and then over that pipe and then carry on. So that's your plan. Well, after making that plan, you actually have to execute it, meaning you need to press the correct buttons at the correct time. Having a plan isn't enough. And after your execution, your mental model is updated based on the feedback. And I separate the mental model in two parts. One is called discovering mechanics, which asks the player to understand or think about what they can do in the game. What are the affordances? What are the mechanics? Does the player know how to jump and so on forth? And the other part of the mental model that the player has is about goals. Does the player know what they should do in the game? And this loop basically carries on at very different timescales, from seconds to minutes, depending on the game. But even before you can engage in this loop, you need to be able to encode your input to the game. You need to be able to press the buttons, right? So if you have one arm, you won't be able to play games that require two hands very easily. So that might be an issue in encoding. And similarly, about putting in what you want, you also need to be able to decode the output from the game. So you need to be able to understand what the game is displaying, whether it's visually, orally, and so on and so forth. So what you see here is the diagnostic taxonomy of failure. I claim that these are the 6 places where a player can fail playing a game. And in a physical manipulation failure, in this case, is execution, right? You decided to pull a piece or move a piece, you have a plan, and you're acting on that plan, but you fail. In Jenga, this execution class of failure is an in-loop failure class, because if you fail in moving the pieces, that is not a design problem. Whereas in chess, that would be an out-of-loop failure. So now, using this terminology, you can take any game that you're developing and then look at what classes of failures are in-loop and out-of-loop. And this capability allows you to basically interrogate your design process more effectively and respond to failures with a little bit more insight. So that was taxonomy of failure. This expanded our vocabulary around failure and helped us identify which ones are bad and good. Let's switch to the next paper, repurposing game AI for inclusivity. And this was presented at AID 2020. Let me just start with the conclusion of this paper. I'm advocating and asking and urging people to use the game playing AIs to assist the players. In the last years, there have been a lot of high-profile victories for reinforcement learning, mainly being able to play games. In 2016, an oral algorithm beat the world's best Go player, and OpenAI and DeepMind basically managed to beat really, really powerful players in Dota and StarCraft, respectively. So when I looked at these results, my initial reaction was like, wow, we can obliterate our players, great. And then after looking at it a little bit more, my designerly side kicked in and I realized obliterating our players really isn't the goal. That's not what a lot of games are about. So it seems like we have a competent game playing AI. It's really good at what it does. Decades of research went into it and a lot of money. And yet we don't want to obliterate our players, but that's what the competent game playing AI does. So the question is, what can we do with this box, right? This black box. And remember, we're not trying to beat the player. That's not the goal. And I claim we should use these technologies to assist our players. For example, in a strategy game, the player can focus on the larger level strategy decisions, and the AI can take charge of the small army unit movement, like micros. Or in a platformer game, the AI can basically show what route to take in an effective way, and it might be up to the player to execute on that plan. Or the AI might watch the game, not necessarily take any action, and after the game is done, the AI might say like, hey, you remember that pass that you did? That was a bad move. It lowered your chances of victory. And then AI can point out the mistakes of the players and actually coach the players to become better. these are all nice and well, but how do we actually come up with these assistance methods in a more systematic way? And that's the second contribution of my paper. It's a design exercise. There are 3 simple steps. We identify the different challenge types. We construct a design space of assistance methods using these challenges, and then we explore the space. Very easy. Let me go deeper into what these actually mean. So identifying the different challenge types. The GIF that you're seeing here is from Celeste. Celeste is a action platformer, and as you can see, the goal of this game is to dodge, climb, run, jump, and dash your way to up a mountain. And the player needs to both plan, meaning the player basically needs to decide what route to take, when to jump, when to dash, and they also need to be able to execute that plan. And you can recognize these terms from the taxonomy of failure. The TOF is a part of this design exercise, but it doesn't have to be. You can pick any challenge types you wish. So after picking these challenge types, in our case, execution and planning, we construct a design space. What that means is we put these challenges on the axes. And the length of these axes represents the magnitude of the game playing AI assistance. So, and the whole space spanned by these 2 axes is our AI assistance design space. So what does that mean? If the AI is helping on the execution fully and helping us on the assistance side or planning side fully, then that's traditional game playing AI. The AI is simply playing the game. But one thing we can do is we can basically tell the AI to only help us in a specific axis, right? AI only help us to plan or only help us to execute. So we can pick a point in this space and see, okay, what would the assistance method look like if it only helped with planning? And that I call Ghost for Celeste. And this is an implementation that we made to test it out. So in our Ghost implementation, what happens is a ghost spawns and it shows the best route to take. And in this implementation, we use A star. But it's up to the player to actually execute that plan. The AI only shows the optimal plan. So what does it look like if we're only helping in execution? Now we call it click to move, where the player decides on which route to take by clicking on the places, but it's up to the AI to go to those places. So the player can just set the path they want to take by clicking, and the execution is handled by the AI. But both of these things, both of these assistance methods are the maximum assistance that we can push in both of these axes. We can also, reduce it a little bit. And this allows us to come up with a variety of different assistance methods. And furthermore, we can even pick spaces in the middle. What does it look like if we help a little bit in execution, a little bit more in planning? What does that look like? So exploring the space allows us to basically come up with assistance methods in a much more systematic way. And that was repurposing game AI for inclusivity. So let's jump into the interventions. The first one is Talent, a framework for dynamic tutorials based on skill items. And this was presented at A 2018. The reason why I made this project was because I was playing Dawn of War, and I was very annoyed by the tutorial. So it was trying to teach me how to move the camera. It said move the camera here, there, in the middle, on the right, and on the left. I was kind of annoyed because, I got it. I was so annoyed that I stopped playing the game, and I decided to, learn how to draw. So I said, okay, let me learn how to draw an owl. I started the tutorial there. I drew my circles. And then the second step was a little bit too difficult. And this I didn't get. And the problem is everyone gets the same help, regardless of your skill level. And Talent is a dynamic tutorial framework that gives you help when you need it and only when you need it. So we can basically support the players who are in need. How does it work? That's 3 steps. First, you define the skills that are used in your game, jumping, dashing, what have you. And for that, we use the skill item theory. Roughly, the skill items have 4 parts to it. They have a player action. Then there's a simulation that is about what the game does in response. And then the player gets some feedback and their model is updated. And after defining your skills, you basically say, okay, here's the skill. And we have a belief on how good the player is in using this skill. So has the player mastered the skill or not? And we have a belief about that. And we update that value using detectors. So what does a detector? They come in many shapes and forms, but this detector is looking at a skill that is about breaking a wall. So this is a breakable wall on the left. And if our character is nearby the breakable wall, but they're not breaking the wall, not making progress, they're loitering, then our belief in their knowledge, in their mastery of how to break a wall decays, goes down. And finally, we trigger in-game events based on these mastery levels. And we made it so that it is usable without coding, and we try to make it very designer friendly because it's up to the designers to actually implement them. So let's see an example. What you're watching now is an example from the default tutorial. The players comes in and they learn how to basically drop from the ledge. And there's no understanding of the skill level. Everyone gets the same system. But with our Talentified tutorial, things are a little bit different. Here on the right, you see different Unity components that allows the designer to customize things as they wish. And when the game starts, one thing that you'll see is a skill mastery level. So there's this ledge drop skill, and our belief in the players knowing about it is 0.45. So it's midway through. When the player is near the ledge and they're not dropping down, our belief in their knowledge of how to drop down decays. And when it passes a threshold, a particle system starts. So it's not as intrusive as just immediately popping up tooltips. But if they still don't take any action, a tooltip starts. And they can drop down, and it will update their belief. So if the player was a master and did not need any help, then the system would just allow them to pass. But if they needed support, the system would pick that up, and that would be that. And in this intervention is actually helping players in the discovering mechanic class of failure. And the final project that I made so far is called SMES. SMES is a tool to adapt dexterity-based games for deliberative play, and we presented that exact 2020. And you can think of SMES as a casual creator for speedrunning. And before we were designing this tool, we actually reached out to our potential users on Reddit, on the disabled gamers and tool-assisted speedrun subreddits were the two parts where we got the most feedback. And we incorporated the feedback we got into the design of this tool. But instead of explaining the game myself, I'll let my coworker explain, Hunter. Let me make sure I'm sharing computer sound. Great. There will be some computer sound, so please lower your volumes if necessary.
Hello. The following is a short video to show you the basics of how the SMES works. The SMES stands for Sharp Multi-Input Editing Software and is meant to help mitigate failure in dexterity-based games. However, we are also excited to see the full extent of its capabilities. Here is our current model of how the tool will operate. Here's the interface before gameplay. To get an idea of how the tool works, let's do a simple movement at first. We'll move to the right and then jump. Here is what the SMES looks like after recording those two inputs. Here, we see a player taking some actions in a platformer game. Oh, but whoops, looks like they messed up their jump. Here's the interface after it has recorded the gameplay session. To the left we see the buttons that are recorded, and in the center we see boxes representing when during the recording that button was pressed and for how long. Along the top, we see a timeline showing when these buttons were pressed since the start of the recording. If we were to press play, we'd be able to replay that set of actions solely from this new recording that the SMES has created. As such, we will still fail that same jump. Let's make some changes. You can use the SMES to change when and what buttons are pressed. Here, let's hold right for a bit longer, press up twice instead of once, and jump a little bit less. Now that we've edited those buttons directly in the SMES, it can replay our new handcrafted recording. Looks like we're still a bit off that jump. That's okay though, we can do this same process again for as many times as we like. Let's go in and redo some things again. Now let's see if this will work. That's it! We were able to clear the jumps. And that's all there is to it. We hope.
That's SMES. Sweet. And I'm going to share computer sound so you don't get annoyed by the ringing. And let's carry on. So what does SMES do? SMES allows games that are all about physical dexterity and execution challenges to be played by those who don't necessarily want to engage it from a very dexterity-based execution way, but rather a more planning aspect. And one thing that we like about SMES is it is tool agnostic or game agnostic. You can effectively use it in some games, many games. Games need to be platformers with short level sequences, but we can talk about the details later on. Okay, so these 4 projects were my past projects, and there are some limitations with these. So the first and the biggest limitation is that there is no evaluation with end users, and unless we test our tools with actual users, it is difficult to say that things work. And up until this point, these have been more prototypes and thought processes, but going forward, we're going to change that. And the second limitation is that the extent and the impact of these AI interventions are rather low. Both in SMES and Talon, we're not necessarily assisting the player in a much more comprehensive way. And as stated before, we can use much heavier machinery to increase the impact of our support. So now let us jump into my proposed future projects. But before that, let's relax once again. And I'm sure this will be very, very relaxing for you all once again. See, it is better this time. And it is better. Okay, but before we move on, let's talk about who am I? I am a PhD student, and hopefully you know this by now. But I'm also a game developer, and I keep making games in mostly game jams about jumping, moving. This one is about pouring police on protesters. I don't know where this came about, and so on and so forth. And I also worked at Ubisoft Montreal at La Forge, and my work was on reinforcement learning. And last summer, I was at Microsoft Research Cambridge Game Intelligence Lab, also working on reinforcement learning. And many fingers crossed, if visa issues are solved, I'll be at Unity working on reinforcement learning. So I have game making experience, and I also have reinforcement learning experience. Why am I telling you this? Because I want to convince you that I have the skills necessary to execute on my proposed thesis. With that, let's look into what my proposed thesis actually is. So I want to develop a reinforcement learning based navigation assistance method, and then I want to test said assistance method. And then this project basically has 4 steps to it. First, I am going to build a first-person parkour game in Unity. Then I'm going to use reinforcement learning to get a competent AI agent that can play the game. After that, we're going to use this reinforcement learning agent to power different assistance methods. And finally, we're going to evaluate the assistance methods, both quantitatively and qualitatively. Let's go deeper at each step. Building a first-person parkour game in Unity. So parkour is the sport of moving rapidly through an area, negotiating obstacles by running, jumping, and climbing. So why did I pick parkour? And how does it look like? So this is the current implementation of my game. In the game, you can jump, you can double jump, and your goal is basically get to the end. You can do some wall running, and I'll be implementing some dashing as well. And you can use these movement abilities to be creative in how you negotiate obstacles. And as you can see, I need some assistance. Right. So why would I make a parkour game? First, navigation is a key player skill in many games. If you have a 3D space and you need to move, well, then the player has to learn how to navigate. Second is, if I discover something useful, discover a useful assistance method, then this can be transferred to many other games. So we can both target a skill that is used by a wide variety of players, but also any progress we make in assisting those players can be transferred to many games. Third, there is a clear separation between the challenges that exist in this task, which is there's execution challenges, but there's also planning challenges, similar to Celeste that we discussed. The player has to decide what route to take, then also actually take it. And it also contains an easily measurable goal. The player needs to go from point A to point B, and that will make evaluation easier. And maybe most importantly, I can actually develop this game. It doesn't require a lot of art assets, and it fits with my skill set. And finally, I can develop a reinforcement algorithm to play this game, and that's important. For this task, I'll be building on top of the FPS microgame Unity template. And this is a translation-based game template. What that means is the game doesn't use physics engine to make the movement work. And I picked this framework among many others, trying to balance these 4 requirements. I need to be fast in developing the game. The computational cost needs to be low. I want to be able to replay the action sequences because I'm interested in using the human play traces as data for my reinforcement learning training, and the project should be shareable. And having an FPS microgame that is well documented and open source actually fulfills all these requirements relatively well. So that's why I decided to make a parkour game. And also, I'm kind of happy that I'm not focusing on combat for once. The second step is to use reinforcement learning to get a competent AI that can play the game. Okay, so what is reinforcement learning? Reinforcement learning is a learning technique where you have an agent. The agent is given a goal. In our case, it will be to reach the target. And the agent actually takes random actions initially to explore the space of what to do. And in that exploration, they somehow stumble upon the goal, let's say. And that gives them a reward. So when the agent learns the reward, they say like, oh, I took this action, I moved towards the goal. It means that that is something good. I'm getting more rewards. And using this formulation, the agent learns what to do. And what's important is there's no handcrafted information. The player doesn't, or the designer doesn't tell the agent how to do what they need to do, but they only say what they need to accomplish. And through simulation experience, the agent figures it out. So why are we using reinforcement learning? First, it handles complex 3D movement with movement abilities relatively well. The current status quo in the gaming industry is to use navigation meshes to handle navigation. And it works relatively well, but there are some limitations. One limitation is that it doesn't necessarily deal with vertical movement very well. But on top of that, whenever you want to add a movement ability, like jumping, dashing, or wall running, a designer actually needs to go in and add a link manually. There are automated ways of doing this, but the traditional way is to get some designers to annotate the map, which means there's a lot of handcrafted information that goes into it. The other reason why we want to use reinforcement learning is because the control model is learned through simulated experience, and that requires no hand authoring compared to navigation meshes. And finally, they can actually be better than the developers and designers themselves, which means if you make a level and you think the best way to finish this level is to jump there and dash there, the game can actually, the reinforcement learning agent can basically show you something that you didn't expect. And that's really exciting. And finally, RL systems can decide on how good a given state is, and that is important. So what do I mean by that? In this task, I'll be using 2 different algorithms. One is called soft actor critic, and the other one is called proximal policy optimization. I have experience in both of these, and they can be assumed to be the state of the art. And both of these methods are actor critic methods. What that means is the AI agent takes in an observation, and the actor neural network, the one on the left, basically, given the observation, given the world that the agent sees, the actor network decides on what action to take. So you can think of it as whether the agent will move forward, move backward, jump, and so on and so forth. But the critic network actually decides on how good the observation is. So you can think of this in our navigation task. How far am I from reaching the goal? How many seconds or minutes would I need to get there? If I'm closer to the goal, the observation, meaning being there, is going to be rated more highly. And that is an important capability, because if we can tell how good being in a state is, then we can use this information to tell the player when they have made a mistake. And this becomes very useful if we want to coach the player to become better. And soft actor critic is an off-policy method, and proximal policy optimization is an on-policy method. Usually, off-policy methods are more sample efficient, so we would go with those initially. But I'm interested in exploring a more recent algorithm called phase equality gradients. And what that allows us to do is to solve two problems. The first problem is when you're training both an actor network and a value network, the training process can interfere, and there can be some problems in training both in a stable manner. And the second problem is that value networks can use the same amount of information much more, meaning you can train that network much more aggressively compared to the actor network, but usually there is no clean separation. And the phase equality gradients paper allows us to fix both of these problems. So what does that mean in actuality? Well, that means that our critic network using the phase equality gradients will be more effective. And if our critic network is more effective, it means that we can coach our player much more efficiently and more accurately. So if we take a step back, looking at the proposed setup from a bird's eye view, the algorithm is going to take some information about the world. It's going to take the relative goal position, where they are, where the goal is, how fast it's moving, some information about the surroundings. And then that is going to go into a neural network. And that neural network is basically going to tell what action to take, go forward, go backwards. And also the neural network is going to tell us how good the observation is. And the visuals that I showed you just now comes from this paper, Deep Reinforcement Learning for Navigation in AAA Games, from Ubisoft La Forge, and my internship project was on this work. So the final results of this paper looks as follows. There's an agent that can move in a rather highly complicated space. They can jump, they can dash. I don't think they can dash. They can double jump. So this is to show that reinforcement learning to solve a highly complex navigation problem is feasible. And I have experience working on this project as well. Okay. And in order to implement the algorithms, I'll be using stable baselines tree, and to make the connection between the game and the learning side, I'm going to use Unity ML agents infrastructure. Okay, so we created our RL agent, and now let's use it to power assistance methods. I'll basically be using the design exercise proposed earlier. And I'm planning on supporting it Wizard of Oz style study. So what that means is, before actually going all the trouble of implementing the AI algorithms, we're going to, a person, me most likely, is going to act like the AI and then test it with actual users. So we can get some insights on what works and what doesn't before going through the troubles of implementing the whole thing. And similar to what we did in SMES, we're going to talk to potential users, for example, over Reddit. And of course, finally, we're going to survey pre-existing assistance methods. And finally, maybe the most important step is to evaluate these assistance methods, both quantitatively and qualitatively. In the quantitative evaluation, we want to ask, are the assistance methods capable of assistance? Meaning, can the learn policy, our reinforcement learning agent, play the game well enough to give assistance? Because if the RL agent isn't working very well, then the assistance that we give isn't going to be useful. And the way we're going to test it is going to be looking at point-to-point accuracy. And we're going to sample these point-to-point accuracy tests from a human playthrough. What that means is a human is going to finish a level, and we're going to pick a point from the human's path and going to say, ask the agent to finish the level. And we're going to measure how often the agent succeeds, hopefully rather high. But we're also going to do some qualitative evaluation. And that is to answer, how effective are the assistance methods in helping the player? Well, do people like it or use it more than a baseline? And the baseline method that we'll be testing is going to be a replay of a static expert solution. So an expert finishing the level, whenever the player asks for help, we are going to play that, replay that sequence, and then compare it to our reinforcement learning-based assistance methods. And our stretch goal is to publish the game and collect telemetry data, do some A/B testing to see how effective our assistance methods are. And that is the final step. So, and with this project, I'll be helping both in execution and planning class of failure to our players. And ideally, when we're said and done, this will result in a paper submission to FDG 2020 that is going to be about the implemented assistance methods powered by RL. And the second paper afterwards would be about the user studies that will be submitted to KaiPlay in 2022. And I mentioned that the limitations of my past projects were evaluation with end users and the extended impact of AI interventions. Hopefully with these proposed projects, I'll be fixing these limitations. And that is the proposed thesis. So the timeline for me flipping these yellow boxes to green looks as follows. In spring, I'm going to develop the Parker game and start implementing oral navigation. I'm already working on it. In summer, I'm going to finalize the agents and implement the assistance methods. Fall, we will start user testing and write the paper on FDG. In winter, I'm going to analyze user data. And hopefully in spring, I'm going to graduate. And after that, hopefully every project here will be the past project. So with taxonomy of failure, we expanded our vocabulary of failure. With repurposing game AI for inclusivity, we proposed a way to use game playing AIs for inclusivity. And with these 4 interventions, we showed instantiations of these ideas. And I claim that hopefully with these 6 projects under my belt, I'll have done enough work to get a PhD. And in the end, let's remember that the main goal is to reduce the feeling of helplessness as seen from the quotes on the screen. And that's it. Thank you very much for coming to my talk on design out helplessness and interventions for game inclusivity. And I am open for your